sklearn, feature extraction, text, description. The sklearn, feature extraction, text module provides tools for converting text data into numerical representations that can be used for machine learning models. This is a crucial step in natural language processing (NLP) because most machine learning algorithms require numerical inputs. This module offers a range of techniques for text feature extraction, including bag of words. BO represents text as a vector where each element corresponds to the frequency of a word in the text. Term frequency inverse document frequency TF-IDF weights words based on their frequency within a document and their rarity across the entire corpus. Hashing vectorizer maps words to integer indices without storing a vocabulary, making it memory efficient. Count vectorizer counts word occurrences in text documents. Inputs. Text data. The input is text data, which can be a list of strings, a corpus of documents, or a single string. Preprocessing options. You can specify various preprocessing steps, such as lowercase conversion, stop word removal, stemming, lemmatization, and tokenization. Outputs. Numerical feature matrix. The output is a numerical feature matrix, where each row represents a text document and each column corresponds to a feature. The values in the matrix represent the frequency or importance of each feature in the corresponding document. Vocabulary. Some methods like count vectorizer and TF-IDF vectorizer provide a vocabulary which is a mapping between words and their corresponding indices in the feature matrix. Steps. Tokenization. Text is broken down into individual words or phrases called tokens. Normalization. Text is transformed into a standard format, e.g., converting to lowercase, removing punctuation, or stemming words. Feature extraction. Features are extracted from the processed text based on the chosen method BO. TF-IDF. Hashing, etc. Metrics. Accuracy. A metric commonly used for classification tasks to evaluate the model's performance. Precision measures the proportion of correctly classified positive samples among all predicted positive samples. Recall measures the proportion of correctly classified positive samples among all actual positive samples. F1 score. The harmonic mean of precision and recall, providing a balanced measure of performance. AUC area under the curve evaluates the performance of binary classification models by considering the trade-off between precision and recall. Mean squared error MSE used for regression tasks to measure the average squared difference between predicted and actual values. Visualization plots. Word clouds visualize the most frequent words in a text corpus. Heat maps illustrate the relationships between features and their importance in the dataset. Scatter plots used for visualizing the relationships between features and the target variable. Fine-tune parameters. Max features. The maximum number of features to be extracted. NGRAM range. The range of n-grams to be considered unigrams, bigrams, trigrams, etc. Stop words. A list of words to be removed from the text. MinDF. The minimum document frequency for a word to be considered. MaxDF. The maximum document frequency for a word to be considered. Uncertainty methods. Confidence intervals can be used to estimate the uncertainty of the model's predictions. Bayesian inference provides a framework for quantifying uncertainty in model parameters. Challenges and fixes. Challenge 1. High dimensionality. BO and TF-IDF can create very high dimensional feature spaces, leading to computational challenges and potential overfitting. Sample use case. A large corpus of text with a diverse vocabulary could result in a feature matrix with millions of columns. Fixes. Feature selection use techniques like feature importance ranking, L1 regularization, or dimensionality reduction PCA, SVD to select the most relevant features. Hashing vectorizer reduces the dimensionality by using a hash function to map words to a fixed size feature space. Challenge 2. Sparse data. Text data often results in sparse feature matrices, where most values are 0. Sample use case. A document containing only a few words from a large vocabulary will have a sparse feature vector with mostly zeros. Fixes. Sparse matrix representation. Use libraries like SciPy's sparse matrices to efficiently store and process sparse data. Sparse matrix operations use algorithms specifically designed for sparse data, such as L1 regularization or sparse PCA. Challenge 3. Handling rare words. Bow and TF-IDF can give high weights to rare words, which might not be informative. Sample use case. A word appearing only in a few documents can have a high TF-IDF score, even if it's not semantically meaningful. Fixes. Smoothing techniques. Use techniques like Laplace smoothing or add-one smoothing to prevent rare words from dominating the feature space. Word embedding. Use word embedding models like Word2Vec or BLOV to capture semantic relationships between words and represent them as dense vectors. Challenge 4. Handling out of vocabulary OOV words. New words not present in the training vocabulary can't be processed. Sample use case. When a model encounters a word it has never seen before, it cannot assign a feature vector to it. Fixes. Unknown word token. Assign a special token for unknown words and treat them as a separate feature. Subword tokenization. Break words into smaller units, subwords, to handle words not seen during training. Word embedding. Use pre-trained word embedding models that cover a vast vocabulary. Challenge 5. Handling different text lengths. Documents with different lengths can lead to biases in the feature space. Sample use case. A short document with high word frequencies might be misclassified compared to a long document with the same words but lower frequencies. Fixes. Normalization by document length. Divide word counts by the document length to account for variations in text lengths. Sentence embedding. Use sentence embedding techniques to represent entire sentences as fixed length vectors, regardless of their lengths. Truncation and padding. Truncate longer documents and pad shorter ones to ensure all documents have the same length.